This video is about Newton's second law of motion. And this law is stated slightly different than probably what you've seen in the past if you've dealt with Newton's second law. And we're just going to kind of start off with what Newton probably originally wrote in some of his early publications when he was kind of coming up with these laws. And it states that the rate of change of momentum of an object is proportional to the applied force to that object and in the direction that that force acts. So to kind of show you an equation of this, well, force is just simply going to be F. The proportionality symbol, something looks like that. Change of momentum. Now the rate of change of momentum. We know rate from earlier when we were talking about the rate of change of velocity was acceleration. So it's like the change in velocity over time. Well, change in momentum. Momentum has a formula mass times velocity, but we want the rate of change of momentum. So it's going to be m delta v all divided by the time. So this eventually will give us something that we would call impulse, but for our purposes, this is originally what Newton's second law kind of stated. Now we've changed that. We know that this right here, this change in velocity over time, is really equal to the acceleration. So rather than putting it that way, we've kind of redone this equation and made it just simply F equals ma. That's the more modern or more probably the way you're more likely to see Newton's second law stated. But it came from this idea that it's proportional to the mass times its rate of change of momentum. And we have to remember that force and acceleration here are vectors. Masses are multiplying constant, or are basically saying that the proportional constant that we have to multiply the acceleration by to get the force is a mass. And that makes this a very kind of famous formula and very useful formula because of that. So it's basically just stating if you apply a force to an object, the object will accelerate in that exact same direction. So let's just say we have, I'm just going to say like a rock. I know that's kind of a weird thing, but we'll say this rock's out in outer space and it has a mass of exactly 10 kilograms. And if I push on this rock with just simply a 5 Newton force, or somehow something pushes on this with a 5 Newton force, what's going to happen? Well, if you use this formula, F equals ma, it's pretty easy to figure that out. So forces, by the way, I got to take a step back. Newtons is a unit here. It's a derived unit. So a Newton is going to equal a kilogram times a meter per second squared. And you can kind of see masses in kilograms, acceleration meters per second squared. So 1 Newton is a kilogram times meter per second squared, and that becomes very useful later on when we're doing things like dimensional analysis. So we'll use those things also here. If I fill in my formula, I have 5 newtons is equal to 10 kilograms times my acceleration, which is what I'm looking for. And now what I'm going to do is I'm going to divide this. Actually, let's convert this. Let's make this 5 kilograms times meters divided by seconds squared. And then if I just kind of recontinue this, 10 kilograms times A, divide that by 10 kilograms. What this does is it makes it very easy to see what happens to our units. Kilograms canceled off, I'm left with meters per second squared. 5 divided by 10, and that, by the way, cancels completely off, so I end up with A is equal to 5 divided by 10, and I'm just going to kind of shift this over here to keep room, 1/2, or 0.5 meters per second squared. And that's a real easy way to kind of see that. The more mass I have, the harder this object will be to accelerate. It'll take more force to create a greater acceleration. Now, the other thing, the new way that this is kind of stated is this is a net force. And let's kind of give you an example of that. So let's take this same rock, and let's just say we can somehow keep this same 5 newtons of force pushing it one way. But maybe now, instead of being in space, it's now in the atmosphere. So let's just say, in the early atmosphere, the upper atmosphere, there might be 1 newton of like frictional force acting against this. Well, this is a pretty simple idea. If you have 5 newtons going to the right and you have 1 newton going to the left, your net force is going to equal 5 minus 1 newtons. Oops, not mn. Change that up. Go back to 10 here. 5 minus 1 is equal to 4 newtons. And we're going to just kind of assume that going to the right is positive, going to the left is negative. So in this case, it's a positive 4 newtons to make that a vector. And if I want to know what the acceleration is now, well, okay, I'm going to take my net force is equal to mass times acceleration. My rock didn't change. It still has the same mass, which was 10 kilograms. So I didn't write that in. So I'm going to say, all right, 4 newtons is equal to 10 kilograms times A. And again, this is 4 kilograms times meters per second is equal to 10 kilograms A. You can probably figure out when you divide by 10 kilograms, that's going to cancel both that unit and that number out. And this 10 kilograms will cancel that unit out. And I'm going to end up with, I'm going to go this direction, A is equal to 0.4 meters per second squared. So it shows if we have less force than we had before, we have less acceleration. So that's what we mean by proportional. The more force, the more acceleration. The less force, and less acceleration. And that, in pretty easy terms, is Newton's second law.